The James Webb Space Telescope has peered further back in time than ever before. What it found should not exist. Galaxies too big, too bright, too soon. If our cosmic timeline is wrong, what else have we misunderstood? Chapter 1. The Standard Cosmic Timeline. When we talk about the universe, we often speak as if we already know its story. Scientists have pieced together a timeline that feels solid, almost carved in stone. But before James Webb began to watch the sky, the script of cosmic history looked like this. The universe began about 13.8 billion years ago with the Big Bang. In the very first instant, space itself expanded at an unimaginable speed. Time, matter, and energy were born in the same breath. The cosmos was hot, dense, and chaotic. For the first 380,000 years, the universe was a thick fog of plasma. Light could not travel freely because particles kept colliding. Astronomers call this the cosmic dark ages. Imagine a vast ocean of particles, but no stars, no galaxies, no light breaking through. Then, something important happened. As the universe cooled, atoms formed, and suddenly light was released. This moment is recorded in the cosmic microwave background, the faint glow that still surrounds us today. It is the oldest light we can see, a baby picture of the universe itself. But stars and galaxies did not appear right away. According to the standard timeline, it took about 100 to 200 million years after the Big Bang for the very first stars, what astronomers call population 3 stars, to ignite. These were giants, short-lived, burning bright and dying fast. They were made almost entirely of hydrogen and helium, with very few heavier elements. When these first stars exploded as supernova, they seeded the universe with heavier elements: carbon, oxygen, iron, the building blocks for planets, life, and everything we know. Their deaths triggered the birth of later generations of stars. Now comes the next major step: galaxies. The models said that galaxies began to take shape around 400 to 600 million years after the Big Bang. At this stage, clouds of gas collapsed under gravity, stars grouped together, and the first galactic structures formed. The earliest galaxies were expected to be small, faint, and irregular, nothing like the beautiful spirals and giant ellipticals we see in the nearby universe today. Around the same time, another key event unfolded. The epoch of the light from new stars and galaxies ionized the surrounding hydrogen gas. For the first time, starlight could travel long distances across space. The fog of the dark ages was lifted, and the universe became transparent. This was a turning point. The early cosmos, once quiet and dark, now glowed with light. Galaxies multiplied, stars were born at a furious rate, and the universe entered a new era of structure and complexity. Supermassive black holes, millions or billions of times the mass of the Sun, were thought to appear much later. Standard models suggested they grew slowly over time, feeding on gas and merging with smaller black holes. It would take billions of years for them to reach the enormous sizes we see at the centers of galaxies today. This script is what scientists taught for decades. It is what textbooks, lectures, and documentaries repeated. And to be fair, it fit well with the observations we had. Telescopes like Hubble gave us glimpses of very distant galaxies, but their light was faint and blurry. We could only see so far and so deep. That is why the James Webb Space Telescope was built, to go further, to look back in time with more clarity than ever before, to test whether this cosmic timeline was correct or not. The expectation was simple. Webb would confirm the timeline, maybe add some details, but nothing too shocking. Astronomers believed they had a solid grasp on when the first galaxies appeared, how stars were born, and how black holes grew. But science has a way of humbling us. Every time we think we have the answers, nature whispers otherwise. Webb was not just going to confirm the timeline, it was going to shake it. Think of it this way. If you find fossils of human civilizations thousands of years older than expected, you don't just rewrite one page of history, you begin to question the whole book. That is exactly what Webb is doing to cosmology right now. Before we dive into those disturbing discoveries, let's pause for a moment. The standard timeline served us well. It explained a lot, but it was always based on limited evidence, on what older telescopes could detect. Webb's mission was to bring sharper eyes to the earliest universe, and when it did, the results were so strange, so unexpected, that many scientists quietly admitted, something is wrong, very wrong. In the chapters that follow, we will explore those surprises in detail. We will see galaxies that appear too soon, black holes that seem impossible, and light that challenges everything we thought we knew about the cosmic dawn. But for now, remember this: the timeline you just heard, the one that begins with a slow, gentle unfolding of stars and galaxies, may not be the true story. It may be a rough draft, a version of events written with incomplete evidence. James Webb has opened the next chapter, and what it found may force us to rewrite the very clock of the universe. Chapter 2: JWST's Troubling Discoveries. When the James Webb Space Telescope began its mission, most scientists expected confirmation of what they already believed. The timeline of the universe seemed secure. At best, Webb would refine some details, give sharper images, measure more distant galaxies, and add footnotes to the story we thought we understood. But from its very first deep surveys, Webb revealed something far more unsettling. Astronomers pointed Webb toward patches of sky that looked empty to the naked eye. Its golden mirrors collected faint light that had traveled for over 13 billion years. Each pixel, each glimmer, was a doorway into the early universe. And what Webb found there shocked the scientific world. Instead of tiny, faint, fragile galaxies, Webb saw fully formed structures, bright, massive, and surprisingly mature, appearing at times when galaxies were not supposed to exist. Galaxies too early, too big. One of the first surprises came from surveys like CEER and GLASS. These programs used Webb's infrared vision to push past the limits of Hubble. In these images, galaxies were identified at redshifts above 12. To put that in perspective, we are seeing them as they were less than 300 million years after the Big Bang. This is incredibly early, so early that, according to the standard timeline, the universe should have been barely ready for stars, let alone entire galaxies. Yet Webb showed galaxies that looked organized, compact, and filled with billions of stars. Some appeared as bright as the Milky Way, even though they existed at a fraction of the age. One discovery, a candidate galaxy known as MAM Z14, has been described as the most distant ever seen, emitting light when the universe was only about 280 million years old. By comparison, if the universe's history were compressed into a single year, these galaxies appeared in the first week of January. That is astonishingly early for such massive structures. The problem is simple: there should not have been enough time. The models predict that stars and galaxies take hundreds of millions of years to accumulate. Gas clouds must collapse, stars must form, and galaxies must slowly grow through mergers. But Webb is showing us systems that seem to have skipped that slow process entirely. Black holes that shouldn't exist. Galaxies were not the only shock. Webb also uncovered evidence for supermassive black holes lurking in the early universe. These are not small remnants of collapsed stars. We are talking about black holes with millions to billions of times the mass of the Sun, according to standard growth rates. Such giants should have required billions of years to reach their size. And yet Webb shows signs that they were already there, massive and active within the first few 100 million years. This discovery is one of the most troubling. Black holes are expected to form from the collapse of massive stars. Then, over cosmic time, they grow by swallowing gas and merging with other black holes. But this process is slow. It is not supposed to produce billion solar mass monsters so soon after the Big Bang. So how did they get there? Were they born massive from the start? Did they form from direct collapse of enormous gas clouds, skipping the normal steps? Or is something deeper at play, something our theories have not yet captured? Too much light. Too soon. There was another unexpected detail. The galaxies Webb observed were far brighter than predicted. Brightness in astronomy usually means two things. Either there are more stars than expected, or stars are forming much faster. In both cases, it suggests that the early universe was far more efficient at building galaxies than models had allowed. Some galaxies had stellar populations that looked surprisingly mature, as if star formation had begun even earlier than we thought possible. That means our estimates for the beginning of the cosmic dawn there. First, light from stars might be off by hundreds of millions of years. If true, this would shift the timeline of cosmic history itself. The JWST program. Much of this disturbing evidence comes from Webb's JWST program, short for JWST, Advanced Deep Extragalactic Survey. JWST is one of the flagship surveys, designed to stare deeply into small regions of the sky for hundreds of hours, collecting faint light from the earliest galaxies. The result is like opening a time capsule. In those images, astronomers can detect galaxies fainter and farther away than anything Hubble ever saw. And what the program has uncovered is forcing scientists to rethink nearly every assumption about galaxy formation. Instead of a slow, gentle process, the early universe seems to have exploded with light and structure almost immediately. A timeline in question. The findings raise a haunting question. If galaxies and black holes already existed so early, are we misstating the universe's timeline, or is the physics itself incomplete? Maybe the models of star formation are too conservative. Maybe gas cooled and collapsed into stars faster than anyone predicted. Or maybe there is something missing from our understanding of how gravity and matter behaved in those early moments. Some scientists suggest that dark matter could have played a different role, creating deeper gravitational wells that sped up the process. Others wonder if our interpretation of redshift, the stretching of light over billions of years, is as straightforward as we believe. Whatever the answer, the message is clear. The timeline we trusted is no longer secure. The emotional impact. What makes these discoveries so powerful is not just the data, it's the feeling they provoke. Science thrives on questions, but rarely does it find contradictions this dramatic. Imagine writing a history book and then discovering ancient cities thousands of years older than your earliest records. That is what Webb is doing to cosmology. It is unsettling. It is thrilling. It is the kind of result that forces textbooks to be rewritten. Chapter 3. Theoretical Earthquake. When the James Webb Space Telescope sent back its first deep-field images, scientists expected clarity. Instead, they got a riddle. The galaxies Webb found weren't small sparks in the cosmic darkness. They were massive, structured, and shining with the light of billions of stars, and they appeared far too early, just a couple 100 million years after the Big Bang. That is like walking into a nursery and finding fully grown adults instead of newborns. Something doesn't add up. The result is nothing short of a theoretical earthquake. Everything we thought we knew about the universe's timeline is now under pressure. Let's explore the leading explanations, each one unsettling in its own way. Hypothesis 1. Galaxies formed faster than expected. The simplest explanation is that galaxies simply built themselves much faster than our models suggest. Maybe stars are born more efficiently than we believed. In the standard picture, stars form when cold gas collapses under gravity. It takes time for hot gas to cool, condense, and ignite nuclear fusion. Models assumed this was a slow, delicate process in the early universe, but Webb's findings suggest a turbocharged reality. Perhaps cosmic gas cooled faster than expected. Maybe dense pockets of hydrogen and helium acted like cosmic factories, churning out stars at 10 times the predicted speed. If so, entire galaxies could assemble in just a few 100 million years. But if galaxies formed this quickly, why didn't earlier telescopes hint at it? Why did Webb have to be the one to uncover it? This leads to a deeper question. Have we been underestimating the efficiency of nature itself? Hypothesis 2. Black holes seeded differently. The galaxies Webb spotted weren't just filled with stars. Some appear to host supermassive black holes, millions, even billions, of times the mass of our Sun. That should be impossible this early. Under current theory, Black holes form from the collapse of massive stars. They start small, maybe a few times the sun's mass, and grow slowly as they consume matter and merge with others. To reach 1 billion solar masses would take billions of years, yet Webb shows black holes that already had that mass less than 300 million years after the Big Bang. One explanation is direct elapsed black holes. Instead of forming from a star, these monsters may have been born fully grown, collapsing directly from gigantic clouds of gas into black holes weighing tens of thousands of suns. If that's true, the universe may have produced black holes in a far more dramatic and chaotic way than we ever imagined. This idea solves the timing problem, but it also creates a disturbing picture. A young universe where black holes, Warren, rare exceptions, but dominant engines shaping everything around them. Hypothesis 3. Our cosmological timeline is miscalibrated. There is another possibility. Maybe the problem isn't the galaxies. Maybe the problem is our clock. When astronomers measure cosmic time, they rely on redshift, the stretching of light as the universe expands. A galaxy at redshift 12 means we are seeing it as it was about 300 million years after the Big Bang. But what if our interpretation of redshift is slightly off? If the expansion of the universe doesn't behave exactly as our equations say, then those galaxies might not be as young as we think. Perhaps cosmic structures had more time to form, and our measuring stick is bent. Alternatively, the speed of structure formation itself might be underestimated. Matter may clump together faster in reality than in our simulations. That would make galaxies appear prematurely massive, when in fact they are simply responding to physics we haven't fully captured. This raises an unsettling thought. What if the Big Bang timeline itself is miscalibrated? What if the clock of the universe is ticking at a slightly different rate than we thought? That would ripple through every calculation in cosmology, from the age of galaxies to the fate of the cosmos itself. Hypothesis 4. New physics, and then comes the most daring explanation. Maybe it's not about faster stars, unusual black holes, or misread timelines. Maybe it's about new physics. Our universe is supposed to be governed by well-understood rules: gravity, dark matter, dark energy. But what if those rules are incomplete? Dark matter, for instance, is assumed to be cold, slow-moving, and passive. It clumps, but only over long timescales. Yet if dark matter behaved differently in the early universe, if it interacted more strongly or collapsed more rapidly, that could accelerate galaxy formation. Another possibility is some hidden force, unknown particles, exotic fields, or dynamics we've never observed might have driven the early universe into hyperdrive. To us, it looks like galaxies are breaking the rules. In reality, the rules might just be bigger than we imagined. This is the most unsettling explanation of all, because it means our current physics is just the surface of a deeper truth. As one scientist put it, either the clock of the universe is ticking differently, or we are missing a chapter in the laws of reality itself. Cracks in the cosmic wall. Each of these hypotheses carries weight. None of them is fully satisfying. If galaxies formed faster, why didn't we predict it? If black holes seeded directly, why haven't we seen clear traces? If our timeline is off, how did we misread it for so long? And if new physics is at play, what does that mean for everything else we take for granted? The truth may be a mix of all these ideas. Perhaps the universe is both faster and stranger than our neat equations. Webb hasn't given us the answers. It has given us sharper questions. What's clear is this: the early universe is more dynamic, more energetic, and more puzzling than our textbooks suggested. Instead of confirming our models, Webb has cracked them open, and the tremors of this theoretical earthquake are still being felt. Astronomers, physicists, and cosmologists are scrambling to adjust. Some cling to old models with patches. Others whisper about radical new ideas. In every case, one thing is undeniable: our understanding of the cosmos is no longer stable ground. Chapter 4. Rewriting cosmic history. When scientists first built their models of the early universe, they imagined a slow and gentle unfolding. After the Big Bang, the cosmos expanded, cooled, and drifted in darkness for hundreds of millions of years. Only after this long silence, they thought, would the first stars flicker into life and galaxies slowly assemble. But the James Webb Space Telescope has shattered that quiet picture. Its data suggests a much more dramatic beginning, a universe that sprinted into complexity almost as soon as it existed. If Webb is correct, our cosmic history must be rewritten from the ground up. So let's imagine what this new timeline could look like. The first galaxies, a sprint, not a stroll. For decades, textbooks placed the first galaxies at around 500 million years after the Big Bang. That seemed reasonable. Gravity takes time to pull gas together. Stars need time to form, and galaxies, vast cities of stars, should be among the last things to appear. But Webb has revealed galaxies shining at redshifts beyond 12. That means they existed just 150 to 200 million years after the Big Bang, far earlier than anyone thought possible. This is not a gentle dawn. It's a cosmic sprint. Imagine waking up to find not a baby universe but one already bustling with massive star clusters, bright structures, and organized galactic forms. The curtain rose, and instead of a whisper, the universe opened with a roar. If this timeline is correct, it changes our picture of the cosmic dawn entirely. The dark ages of the universe may have lasted only a fraction of what we once believed. The stars came on like floodlights, not candles. Black holes, born beside galaxies in the old model. Black holes were latecomers. First came stars, then galaxies, and much later, black holes grew slowly inside them. They were thought of as the byproducts of cosmic life, not its co-creators. Webb's data tells a different story. We now see supermassive black holes in galaxies that are impossibly young. This suggests black holes were not waiting on the sidelines. They were born at the same time as galaxies, perhaps even shaping them from the start. Think of galaxies and black holes not as parent and child, but as twins, born together. Each influenced the other, locked in a coevolutionary dance. The black holes fed on surrounding gas, while their immense gravity sculpted the galaxies around them. This flips our understanding upside down. Instead of galaxies slowly nurturing black holes, it may have been black holes that helped galaxies grow. The epoch of reionization. An earlier, longer-era astronomers once believed the epoch of reionization, the time when the first stars and galaxies ionized the fog of hydrogen that filled the cosmos, began around 500 million years after the Big Bang and ended about 1 billion years later. But if galaxies and black holes were active at just 150 to 200 million years, then reionization must have begun far earlier. It may also have lasted longer, stretched out as these energetic young galaxies blasted their surroundings with radiation. That would mean the cosmic fog cleared much faster, allowing light to travel freely across the universe far sooner. This paints a picture of a universe that went from opaque to transparent in record time. Another sprint, where we once imagined a crawl. How the textbooks would change if JWST's data forces us to abandon old assumptions. The way we teach cosmic history will have to transform. The cosmic dawn, once described as a quiet spark, it would now be taught as an explosive surge. Instead of a slow sunrise, it was a sudden blaze. Galaxies and black holes, once taught as sequential, they will now be described as partners. Born together, they grew together, each shaping the other from the beginning. The universe's growth, once thought of as gradual and orderly, it will be retold as chaotic, fast, and unpredictable. The difference is like opening an archaeology book and discovering that human civilizations existed thousands of years earlier than we believed. Suddenly, the entire story of human history would need rewriting. That's what astronomers now face with cosmic history. Philosophical impact, a roaring beginning. For centuries, humanity has looked to the stars for meaning. The Big Bang was often described as a single spark, followed by a long silence, and then the slow rise of order. It was a comforting story, a universe that grew like a child, step by step, into maturity. But Webb suggests something far less gentle. The universe may have been loud, fast, and explosive from the very beginning. Instead of whispers, it roared into being. This raises unsettling questions. If the cosmos can leap ahead so quickly, what else might we be underestimating? If galaxies and black holes appeared in lockstep, what deeper forces are at play? Science thrives on questions, but these are not minor adjustments. They are profound cracks in the foundation of our cosmic story. The human analogy. Let's use an analogy closer to home. Imagine archaeologists digging into the earth. For centuries, they believed the first human civilizations began around 5,000 years ago. Then one day, they uncover a city buried deep underground, complete with architecture, writing, and culture that is 20,000 years old. This would not just add a new chapter to history, it would rewrite everything we thought we knew about human progress. That's what Webb is doing to cosmology. It isn't simply adding details. It's forcing us to rethink the entire narrative of the universe's first billion years. Chapter 5. What this means for us. The James Webb Space Telescope was designed to look deeper into space than ever before. But in doing so, it may have forced us to look deeper into something even more unsettling. The foundations of our understanding. We expected Webb to confirm the grand story we've been telling for decades. A universe that began with the Big Bang, slowly cooled, and then built galaxies piece by piece. Instead, Webb has revealed cracks in that story. Galaxies appearing too early, black holes growing impossibly fast, a cosmic dawn that doesn't match the script. So what does this mean for us? Not just for astronomers, but for humanity itself. If the timeline is wrong, our entire picture of the cosmos rests on a handful of models. The CDM model, lambda cold dark matter, is the reigning framework. It combines dark energy, lambda, cold dark matter, and the physics of cosmic inflation to explain nearly everything we see. This model predicts how galaxies should form, when stars should appear, and how the universe should evolve. For decades, it fit the data beautifully. But Webb's discoveries suggest something is off. If galaxies and black holes existed far earlier than the model allows, then the timeline itself may be broken. And if the timeline is broken, so is the model. That would mean inflation, dark matter behavior. Even the way we calculate cosmic expansion may need revision. We might not just be patching the equations. We might be opening the door to an entirely new understanding of reality. New physics. The door cracks open whenever old theories strain under new data. One possibility always lurks in the background. New physics. If Webb is correct, the laws we rely on might be incomplete. Maybe dark matter isn't as passive as we thought. Maybe new forces shaped the early universe. Or maybe our very idea of time in the cosmos is What if time itself flows differently on cosmic scales than we've assumed? What if redshift, the very tool we use to measure the universe's age, is whispering a truth we don't yet understand? These aren't idle speculations. They're the kinds of questions scientists must now confront. Because when the evidence defies the framework must change. And that is both terrifying and thrilling. The fragility of scientific consensus. There's a lesson here that reaches far beyond astrophysics. Science is often spoken of as solid, settled, and certain, but in truth, it is fragile. Consensus is not carved in stone. It is a snapshot of what we think is true, until new data arrives. The history of science is filled with moments like this. The Earth was once thought to be the center of the cosmos, then the Sun, then the galaxy. Each time, new evidence forced us to step back and redraw the map. Webb's findings may be the next great shift. They remind us that our most trusted theories are always provisional. They work until they don't, and when they fail, humanity must be willing to rewrite its story. This is not a weakness of science. It is its greatest strength, but it's also humbling. We do not live in a universe that conforms to our expectations. We live in a universe that surprises us, again and again. Humanity's role in rewriting the cosmos at its core, This is more than a debate about galaxies and redshifts. It is a story about us. For as long as we've looked up at the night sky, we've tried to explain it, first with myths, then with philosophy, now with physics and telescopes. Each time, the story changes. Each time, the horizon expands. The James Webb Space Telescope is not just a machine floating a million miles from Earth. It is a mirror, reflecting back our endless drive to question, to doubt, to search. With every discovery, we are forced to rewrite not only the story of the cosmos, but our own place within it. What does it say about us that we build instruments capable of challenging our deepest assumptions? It says we are restless. It says we cannot accept easy answers. It says that humanity's role is not to settle the universe's mysteries, but to chase them, even when the answers unsettle us. Awe, hope, and doubt. So where does this leave us? In a place of tension, balanced between awe, hope, and doubt. Awe, at the scale of what Webb has revealed. Galaxies too early, black holes too massive, light too strange. Hope that these mysteries will open the door to deeper truths, perhaps even a new era of physics. Doubt, because every answer raises more questions, and because what we thought we knew may be far less certain than we believed. This tension is uncomfortable, but it is also where discovery lives. Closing hook, James Webb did more than look deeper into space. It may have looked deeper into time, and in doing so, it uncovered a truth we are only beginning to grasp, that the universe's story is far stranger, far faster, and far more mysterious than we ever dared to imagine. The question now is not just what is out there, but what is real. And as we stand at the edge of this mystery, one thing is certain. The story of the universe is not finished. It is still being written, and we are the ones holding the pen. If this journey into cosmic mysteries made you question what you thought you knew, consider leaving a like, subscribing, and sharing your thoughts in the comments. After all, the story of the universe is still being written, and so is ours.